start my lecture. Thank you.
Start his lecture.
Thank you. Okay, so thank you very much, Sandip. I have to say that I can't thank the organizers since I'm nominally one of them. But I'm actually standing in for Kyriakos, who was supposed to give these lectures, but who couldn't come at the last minute because many of my friends, including some in this institute, have a bad habit of not maintaining valid passports. But other than that, okay, so I'm going to try and fill in for Kyriakos as best as I can. So the objective of these lectures is, to talk about some old versions of, paradoxes associated with black holes and the quantum aspects of black holes. Okay, so usually, in these schools, it's conventional to talk about the most recent cutting-edge stuff. But we thought it would be useful to also have some discussion of some older problems that in fact have not received a lot of attention recently, but at least I think are deep and are probably telling us something deep about quantum aspects of black holes. And so I'm going to speak about papers which are about 10 years old, but I think which lead to scientific questions that are still not completely and properly understood. So in this lecture, I'm going to talk about these papers by Almeri, Marolf, Polchinski, Sully, and Stanford, and then there's a summary that, some additional things that we did with Kyriakos. And one paper that's relevant is this. Some of this was also, recapped in a review that I wrote, and this is section 6 of that review. Okay. And the basic theme is going to be about paradoxes with large ADS black holes. And state dependence. Okay, so that's what I'm going to talk about. As I said, this is not a topic, and that's why, as you can see, the references that I'm giving are somewhat old references. And so, there's some newer stuff to say that I'll try and say tomorrow. But a lot of these are just, old open questions that are important, but that we haven't made much progress on. And so I'm going to try and give you a flavor. There are only 2 lectures, one today, one tomorrow, of what these questions are. Okay. Now, before I go on to what these questions are, I want to emphasize what these questions are not. Okay. So, in particular, you will notice that in this, I do not have any reference to the original paradoxes by Samir Mathur and AMPS, which is without the last S. Okay. These paradoxes, which were in fact first set up by Mathur and then elaborated a little by AMPS, are paradoxes that have received recent attention, and the objective of these lectures is not to talk about them. So let me tell you what this paradox is quickly and what we've learned about this in recent years, and then I'll go on to talk about what the main topic of these lectures is. So the way the Mathur or AMPS original firewall argument goes, by the way, just to say, of course, goes without saying, please interrupt me whenever you need to, if I'm not being clear. Yeah? So I want to tell you what I'm not talking about, and I'll recap quickly how these paradoxes went. The way these paradoxes went were to say, think of a black hole, which is an old black hole. Okay? And if you look at the old black hole, then you can argue that if you look at degrees of freedom just outside the black hole, which corresponds to the new radiation, then these degrees of freedom have to be entangled with degrees of freedom far away. And so B has to be entangled with C. You can argue that based on some general arguments. But just the derivation of Hawking radiation that Raghu covered in his lectures tells you that B also has to be entangled with A. And this leads to a paradox with the monogamy of entanglement that, as I said, was first pointed out by Samir Mathur. And that led to discussions that maybe the interior doesn't exist and so on. However, I think now we have a pretty good understanding of how this paradox is resolved. And the resolution is simply that, degrees of freedom in A should be identified with some complicated combinations of degrees of freedom in C. Okay, so this identification is some complicated identification. So simple operators in A become complicated operators in C. But we understand this from many different perspectives. We understand how this follows very generally from the constraints of gravity And in fact, in the island computations that I think Raghu hasn't yet discussed, but we'll discuss, so hopefully Alok will discuss some of this tomorrow, and will explain how, a phenomenon of this kind, where degrees of freedom here get identified with degrees of freedom far away, follows from the gravitational constraints. And I think Raghu also has a lecture left, and in a different setting where you couple the black hole, allow it to evaporate by coupling it to a non-gravitational bath, you get the island proposal, and in that as well, the degrees of freedom, the entanglement wedge of the radiation region includes some part inside the black hole, which is the island, and so it also, follows in different settings from all the recent work on the island proposal and the page curve. Okay, so we understand this in many different ways, and I don't think this paradox itself is a, this is something very interesting about gravity. In fact, I spent some of the past few years thinking and trying to understand this better, and many people here have spent some time trying to understand this better. So this is something that's very interesting. It tells us that gravity somehow, observables in gravity are localized very differently from the way we think observables in quantum field theory should be localized. And so this is probably also deep, but I think we understand this well. And so the objective of the lecture today and the lecture tomorrow is not to discuss this physics, but to discuss a separate set of physics which had to do with large black holes in typical states and the eternal black hole, which in fact is not resolved by just recognizing this loss of locality in gravity. Okay, so that's the objective of what I'm going to talk about. Are there any questions of where we are going to go, and then I'll say more stuff in detail. Yeah.
Is this the same as complementarity?
Yeah, it used to be called complementarity. What used to be called complementarity sometimes was, I think, not used in a very precise sense. Sometimes it was said that, there are different descriptions for different observers. One observer falls in will see something, some observer falling somewhere else will see something else. I think now, we have some more precise operator identification. So I can tell you how the operator, or the effective field theory operator here, you would write down as a version of operators here. It's still true that, an observer falling inside would see nothing. And, someone making very complicated measurements here could affect something here. So all those things are still true, but it's one version of how you could have interpreted the old statements about complementarity. Yeah. Also, maybe one more thing I want to say is this is a more general feature. It doesn't necessarily apply only to black holes. So this kind of physics where, some degrees of freedom here can be written in terms of degrees of freedom far away, also applies, is something you can check in just empty space, so in empty ADS. So, black hole complementarity somehow suggested there was something special about black holes, and this happened in the presence of black holes, but that's not true. It's just a general feature of gravity that degrees of freedom in some region can, in a bounded region can be identified with degrees of freedom in the complement of the bounded region. So this we understand well, but yeah, and it's not, yeah, so maybe in that way it's not quite black hole complementarity. It's true it holds in black holes, but also holds separately from black holes. Yeah, I don't want to, yeah, okay, go on, yeah. Maybe Raghu will discuss the paradox. I don't, yeah. The paradox was, as I said, this is not the topic of the lectures. The paradox was that think of a black hole, okay, and think of the region just behind the horizon. This is my cartoon of the horizon. And the region just outside the horizon, and the region far away. Then you can make an argument, I'm not explaining the argument right now, but you have to trust me, you can make an argument that degrees of freedom just outside have to be entangled with degrees of freedom far away. But you can also make an argument just from the derivation of Hawking radiation that Raghu already discussed, that the degrees of freedom here also have to be entangled with degrees of freedom here. And entanglement has a monogamy property, which is that a single degree of freedom can't be entangled with two other degrees of freedom. You can make this precise in terms of monogamy of Bell correlators or strong subadditivity of entropy and so on. This kind of setup looks like it leads to a contradiction with that. And the resolution is that you should realize that these degrees of freedom are the same as these degrees of freedom. These don't commute. And because they don't commute, there's no paradox with monogamy because, you shouldn't think of this and this as separate degrees of freedom. It's entangled with the same qubit. Yes. Yes.
And I should know this, but do you know the map well enough to know how complex the reconstruction outside is?
Yeah, I think we know the map fairly well. I mean, I could write down some explicit version. We can do the, yeah, I can explain this to you. And as I said, we can check this also in empty space. And there are various kinds of maps. The map that I like is one where you put I can explain to you. You put some projector and you write down some other operators that come from the Richtlieder theorem, but you can write down those operators explicitly. So it's in the presence of black holes, it's a very complicated map. It involves insertion of order n squared kind of operators. In empty space, it's simpler, but still a complicated map. But I think we do understand that. Okay, good. So the object of these lectures is to talk about something else, okay, that we haven't been exploring so much recently. And it's to talk about typical states in ADS-CFT. So, these lectures are really going to be in the context of ADS-CFT. And I'll try and explain maybe at the end of this lecture or tomorrow why, in fact, the paradoxes that I'm now about to describe do not occur for flat space black holes. Okay, so these paradoxes are all for ADS black holes. Okay, they're not. I don't know of any version of the paradoxes I'm about to outline that exists for flat space black holes. This paradox you could set up for a flat space evaporating black hole, okay? But not these ones. At least I don't know how to do these ones for flat space black holes. Okay, so let me introduce some notation. So let psi be a typical state with the property that its energy is much larger than n squared. Okay, much larger doesn't mean parametrically larger, it just means 10n squared or 100n squared or whatever. Okay? Just large enough that you know that the dual state is a large ADS black hole. Okay? When I say typical state here, there's a precise sense in which I mean typical. It means that, let's say you fix the energy of the state psi within some range. So you decide that you want the energy of the state to be between 100 n squared and 100.1 n squared. Okay? Then there are a lot of states in that regime. There are exponentially large number of states in that regime. Then you can define on that Hilbert space a Haar measure, okay, which assigns volumes to regions in the Hilbert space. And then you can say, using that Haar measure, you pick some state. And that's what I mean by typical state. And then we'll ask questions about that. So there are always some states, even at this high energy, some exponentially small number of states that might not correspond in the bulk to large ADS black holes, but we expect the typical states do correspond to large ADS black holes. Okay? At least outside, and then we'll say something more about inside. No, psi is not an eigenstate of anything of the energy. Yeah. This is the expectation value. Not an energy eigenstate. In fact, eigenstates, so that's a good point. Eigenstates are never typical. Eigenstates are measure 0 in the Hilbert space because there are only e to the n squared eigenstates, volume is much more. So, any basis that you pick is always measure 0. So in general, we don't want to be on any element of a basis. Okay, yeah. So I didn't understand. I mean, they should what? Actually it doesn't matter so much if they are special, but we want to make statements for most states. That's the flavor of what I'm saying. For instance, you could do what Matt said and say, let me think about a big energy eigenstate. And there's nothing that's very wrong with doing that. But, what I want to argue is that it's, the paradoxes I'm going to set up are paradoxes that will work, that will work provided you agree that most states have this dual. So let's say I found a paradox for energy eigenstates. Then you could tell me, oh, energy eigenstates don't correspond to large ADS black holes, they're kind of singular, but most states do. Okay, so that's why I want to in fact be in the most general condition. There's nothing bad in fact if you choose energy eigenstates or something else. Any other questions? Okay. Yeah, so the statement is that if you pick a typical state with high energy, then you expect that the dual of most high energy states is a large ADS black hole in the bulk. So, large ADS black holes dominate the microcanonical ensemble. There is, of course, some probability that the dual state is not a large ADS black hole. That's why I want to be for a typical state for which the dual state is a large ADS black hole. For most states, the dual state is a large ADS black hole. So for most states, and most here is precise, it's exponentially large fraction of the volume.
So the rest of them is like particles very close to the boundary or something like that?
The rest of I don't know what the rest of them are, but maybe you come up with some gas or stuff. I don't know what the other kinds of states are. You can always come up with some states that have the same charges as the black hole, but which are not black holes.
You can have stuff very close to the boundary, very high.
For instance, okay, maybe. Yeah. The large ADS black hole does correspond to pure state. Yes, this is a pure state in the CFT. Indeed, so it's a dual of a large pure state, we expect would be a large ADS black hole. It's a black hole that formed from collapse. So you had ADS in the far past, you did some, the way you'd produce such a state is, you take ADS, you turn on some source, all the time keeping the state pure, you inject some energy, you let the state collapse to a black hole, then you manipulate it or you do something else, never making the state mixed, always keeping it pure. And that kind of thing will eventually, if you wait an eternity, not an eternity, but a long time, will turn into a typical state. So that's the kind of process by which you would prepare such a state in the bulk. You would allow for collapse of a pure state and then wait for a long time.
Suvrat, are you?
Covered in the computer science lecture that was given here.
I must admit, I was not present for the computer science lecture, so you have to tell me what was said, yeah.
There's a concept of typical sequences.
This is not, it's not a sequence. I'll give you a simple way to think about it. There are lots of energy eigenstates, right? So just take some sum and just take these numbers to be some random numbers that square to 1. So take a state between energy, some number like, let's call it kn squared to kn squared, k plus delta n squared. Okay, so it's in some range, this energy. Take all the energy eigenstates there and just take a sum of them, so the sum mod of ai square is 1. And then just pick ai's as you like. Okay, pick ai's in some random way. That's all I mean by typical state. It's not such a deep concept. There's a question, yeah.
Yeah. So you're basically saying that above the Hawking page temperature,
Yeah.
most states are black
holes. That's all I'm saying.
There is these ADS solitons also, no?
Exponentially atypical, surely. You could have, there could also have states like what Matt was discussing, where you have some particles sitting very close to the boundary that have high energy. But, most states we expect are black hole states.
It's not obvious, though.
Well, so most states have to have, from the fact that we can count the entropy using ADS CFT, it is clear that this should be the case, because otherwise the entropy calculations would not have worked. They would be counting the entropy of these solitons and so on. There's one more thing. We should realize that there's one more feature of typical states. It's just kinematic. It happens in all large Hilbert spaces. It is that typical states are always close to each other for simple observations. So if you look at the metric in one typical state, it is exponentially close to the metric in another typical state. Therefore, what this tells you is there is a universal bulk geometry which is dual to a typical state, to all different typical states. Now, it's very unlikely that universal bulk geometry is an ADS soliton, much more, is the ADS black hole. Even in cases where we haven't successfully managed to match all the subterms in the entropy and the coefficients, we still expect that, it's not that there's another universal geometry that dominates over the black hole entropy. Yes? There's no entanglement, they're just pure states. You can define a temperature by looking at the density of states and differentiating with the energy. But there is no bipartite division I've made here. Of course, if you made a bipartite division, you would get a page value. So you could take the boundary theory and you could make a bipartite division there, it would follow exactly the page. No, they're random states of exactly the kind that Page considered in his paper. So they're hard typical in exactly the same sense that Page had when he discussed average entropy of a subsystem. Okay, good. So there's a bulk black hole. I'll just write down the metric once. We're not going to use this metric very much, but In fact, the black hole is a Schwarzschild black hole. Okay, it's most of the volume is in fact taken up by Schwarzschild black holes, which don't have much angular momentum or anything else because we are looking at typical states. Okay, where this mu is the mass parameter, it's related to the mass with some factors that we don't care about. And as you can see, asymptotically far away, this becomes EDS. This is my R, which looks like a V or like a gamma, but it's an exercise for all of you to figure out what that is. So this is F of R. Yeah. Okay. Good. Okay. So here's the question we want to ask. Yeah? Do there exist in the CFT, okay, so we are looking for CFT operators. Do there exist some operators which are labeled, these xi's are some coordinates r, t and omega. Do there exist some operators in the CFT that have the property such that for n much smaller than n, n is, the small n doesn't scale like capital N. Where this G is as computed by bulk EFT. Okay. So what am I asking for? I'm asking, are there some operators in the CFT that can play the role of local observables in the bulk? Okay. How do I check that they're correctly playing the role of local observables in the bulk? When I sandwich them in this state, I take a product of them, I compute the expectation value, and I ask, is this answer the same as doing a bulk computation using QFT in curved spacetime in this geometry? That would have given me some answer for correlators of quantum fields. And as do I get the same answer up to some order in perturbation theory? In fact, in this talk, we'll almost always be at first order in perturbation theory. We'll never go beyond that. We'll just at some point use the commutator of the Hamiltonian. But in principle, you could ask for these operators to be made as accurate as you like up to 10th order in perturbation theory. Importantly, I'm not asking for these operators to make sense non-perturbatively. I'm just asking, at least at the free field level and at first non-trivial order in perturbation theory, can you find some operators in the CFT that can play the role of local bulk operators? Okay? And local bulk operators means they give you the same answer that you would get by doing bulk EFT computations in this geometry. So that's the question that I'm going to try and address. It sounds like a pretty simple question, but that's the question that I'm going to try and tell you. Turns out to be quite subtle when you take these points xi's to be behind the horizon. Xi's are bulk points. They're just labels for the CFT operators. They're bulk points, but you can always take a CFT operator, and I want a 4 parameter or whatever parameter family of CFT operators which are labeled by these xi's which have that property.
So the field phi's, are they in the bulk or in the bound?
No, the fields phi's are CFT operators, but they're labeled by some numbers that I want to interpret as bulk coordinates so that when you insert them in the CFT, something you can do in compute, you will find an answer that corresponds to what you would have found if you had done the bulk computation. Okay, that's the question we want to ask. Because I don't want to demand that this should work for very, very large n. Someone might say that if you take n to scale like capital N, then the bulk description completely breaks down. You can't trust this side at all. That's why. Okay, so in fact, we'll only be looking at 2-point functions and 3-point functions. So nothing, we're not even going to take like anything very large. Okay. So it seems like a very reasonable requirement. Yeah.
So you might come to this.
Yeah.
Even outside the horizon, I know, of course, at the generalized free field level that you can do HKLL.
Yeah.
But if you include interaction,
then also we believe you can do HKLL. So HKLL, in fact, Kabart and Lifshitz, K and L have papers on this, on improving HKLL in the presence of interactions. But it's pretty clear that it should work in principle. They've actually written down more concrete formulas, but it's not hard to see that it must.
the same.
Yeah, you kind of solve the bulk equations of motion perturbation theory. So you have the free field answer and then you solve the bulk equations sort of order. So you get. Yeah. Okay, so this is question 1. Now, this question is called the question of typical states, okay, and the fact that these operators are going to turn out to be subtle is sometimes called the typical state paradox. However, there's an important point I want to make in these lectures, which is that, for typical states, sometimes people are agnostic and they might say, okay, fine, typical states don't have an interior, typical states have firewalls, maybe typical states have 50% firewalls, 50% black holes, 50% white holes. However, a point that I want you all to take away from these lectures is that the same paradox also exists for the eternal black hole. Okay? So in particular, let psi TFT this is the thermofield double state. Okay. This state, I'm going to write an orange because this chalk is very dusty. Let this be the thermofield double state. Okay, this is the canonical example we have of ER equals CPR, and we believe that this state is also dual to this geometry, but not to a one-sided geometry, but to a two-sided geometry. Okay, so we think this state is dual to a two-sided bulk, where you have two CFTs, a left CFT and a right CFT, and we think this state is dual to this kind of a geometry. Okay. So I'm going to ask the same question about this state. So we'll ask the same question. Can you see if I write an orange because the white chalk is very dusty? You can see? Okay. Same question means, I'm going to ask this question. Yeah. Do there exist operators which have the property that when you insert them in this kind of state, I'm going to make one more physical requirement, I'll come to that by later in this lecture. You demand this, can you find operators that work correctly in the thermofield double state? So we'll see the paradox is actually deep because it's not just a question of saying something or not saying something about typical states, about which some people might choose to be agnostic, but saying something about the thermofield double state that we think we understand well in many different ways. Okay, so I'm going to try and explain how there's a paradox also for the thermofield double state. And this again is a point that I think is not emphasized sufficiently. Even now when people rarely talk about the typical state paradox, very few people talk about the paradox with thermofield double state. So please, if there's one point I'd like you to take away, this is one point. Remember there's also a paradox for the eternal black hole. Yeah?
Isn't thermofield double an example of a typical state?
No, because this is a state in a single CFT. So when I said state here, I was talking about a superposition of energy eigenstates, which were pure states in a single CFT. This is not a state in a single CFT, it's a state in the tensor product of two CFTs. So this is a state of two CFTs. Okay? So a thermofield double state is not typical. It's not typical, by the way, even in the Hilbert space that corresponds to two CFTs because it's entangled in a particular way. The energy eigenstate is entangled with energy eigenstate. So thermofield double states are not typical states in any sense. They, first of all, don't even belong to a single Hilbert space, but even in the direct product Hilbert space, they're not typical. Yeah. Go on, yeah. Or either way, yeah. Yeah, you can take phi to be whatever you like. You just. Yeah, it can be. So you can find whatever operators you like. I'm going to give you some general arguments. What restriction? No, it makes sense because it makes sense on the right hand side. The right hand side is a low point function computed in effective field theory. Left hand side, I didn't say anything about what these phis were. I didn't say they were generalized free fields or anything. I just want some operators, which you'll produce for me, that have the property. When I put a few of them, they give you the same answer as you get from the right hand side. The right hand side n is important because I'm doing effective field theory computation. So I don't want to compute very high point correlators. On the left hand side, you can do whatever you like to give me the operators. Yeah. No. The paradox is for typical pure states. I haven't come to the paradoxes. How do you know I could have taken a mixed state? The paradox is for typical states. I'll come to the paradox. The thermofield double state is indeed a mixed state on one side, but it's a particular example of a mixed state on one side that we understand well, where the entanglement is very special. So we think we understand the state well. It's really dual to this geometry. It's not dual to this and a very long wormhole and something else. Okay? So we think we understand this thing well. And this is a pure state. It's not a mixed state. Yeah. This beta would be just del S by del E, so it would just be a derivative. There's no temperature as such because it's not a mixed state, but you can always look at the density of states, and you can use that to define an effective temperature. So if I computed correlation functions here, they would look by the equivalence of ensembles like correlation functions in the microcanonical ensemble at this energy E, and then by the equivalence. So first, these typical states are exponentially close to correlators in the microcanonical ensemble that you can just prove kinematically. It doesn't require ETH or anything. And then by the equivalence of ensembles, those microcanonical correlators are dual to correlators in the canonical ensemble with beta associated with del S by del E.
Yes, the reason I'm asking is because typically in this kind of pure state that you are completely random, you are defined, they call it infinite temperature.
It's not infinite temperature because I've limited the energy. So it's finite temperature. So there is a finite value of del S by del E, which I can associate with beta.
So you are saying basically AI could be random given that constant.
Given this, yeah, this I is summing in this range. So I've limited the energy. So it's not infinite. It's not completely infinite. There's a finite temperature associated with this. Yeah. What? So the outside will certainly look like a swatch. So this question right now I'm asking for both outside and inside. I will show you that for the outside there's no problem in finding these operators. That what?
How do you argue that they don't have a second boundary? Because outside they look like a short circuit. You think you can continue?
Well, so right now we are only asking the question of, I will show you that outside they will look, it's easy to find operators that look like the Schwarzschild black hole. Then we are only going to ask, can you go a little bit inside the horizon? Not very deep. Well, so let me come to the paradox, then you can ask where it should break. Right now I'm just asking, I'm going to ask this question, right now I've not made any statement. Do there exist such operators or not? So that you will get the values G as computed in this geometry. That the question is clear, right? So we can either see whether we'll get these operators or not. I'm going to argue to you.
One CFD
Oh, so then your answer would be you wouldn't get such operators. Instead, you would get operators with G corresponding to some different geometry. Maybe, but I think we'll run into trouble just behind the horizon. So it's not like you'll have, that option will not help you.
So in number 2 are the phi's on both sides or just on one side?
This guy?
Phi, the operator.
Phi's could be on both sides in number 2. I'll allow phi to be on both sides. Yeah. Well, so that's the point of the talk of the lectures is about state dependence, which is what I wrote there. Yeah. Yeah. So right now, so indeed, the point I want to explain at the end of this lecture is that if you insist that these phi's are just ordinary operators, then you'll run into a paradox. If you allow them to be state dependent, you can indeed find such operators, as I'll explain tomorrow. But then you have to deal with the issues that have to do with state dependence. So indeed, the point is to discuss some of the subtleties with state dependence, but also lead to the question of why it is required.
So if it's not almost always true.
Yeah, it's fine if it's almost always true. It's fine. Yeah, you can make it almost always true. So you can make it work for almost all states. You mean that's fine? If you can find such operators, that would be fine.
You'd be happy.
I'd be happy. I'd be happy. If you found ordinary operators that work for almost all states, I'd be happy. In fact, yeah, so it is important that, in fact, you do expect it to work for almost all states. When I say typical state, I'm not being very precise. What I really mean is that, you expect it to work for all states except for an exponentially small number of states. So it's fine if it's almost always true. Yeah. No. Typical state is not a collapsing black hole. It's very important. Is that what that was the question? No, typical states are not collapsing black holes because collapsing black holes are those states where if you evolve them a little bit back in time, you get a big excitation on the boundary. So that's a very special state, a state which has collapsed in the recent past. So typical states are states that collapsed in exponentially long time in the past. So you evolve them both forward and backward in time, nothing special happens. Yeah, they can be anywhere inside also. So collapsing black hole is not a typical state. But you can take a black hole form from collapse and wait for a little time. That's not still a very typical state if you wait for scrambling time a little bit longer. But we'll set up these paradoxes really for typical states. Okay, good. So I hope that sets this thing. And indeed, the answer we are going to reach, as Tom anticipated, is, let me write it here. No, if are ordinary linear operators and yes, if they are state dependent. But yeah. Sorry. Okay. Let me try. Actually, there was no blue, it was pure state of orange. It just looks mixed as this one, but okay.
What is linear?
Linear operator just means an operator of the usual kind we see in the postulate of quantum mechanics, which just acts, it's a matrix on the Hilbert space, that's all. Yes.
Can you repeat this? Can you purify it?
Huh?
I can't read at all.
Okay, I'll purify it. I'll just write it again. Well, yellow works better? Yeah, there's some yellow. The white is incredibly dusty, so I don't like the white. Answer is going to be yes or no if phi xi are familiar linear operators and yes if they are state dependent. Now, the reason I want to go through, one more point I want to make is, there's been a bit of a sociological shift in some sense, because when we first talked about state dependence, it was considered very unusual, and now there's a lot of use of state dependent operators. But I think that some of the scientific questions have still not been resolved, and that's why I want to emphasize this point, and I want to go through these issues. And tomorrow I'm going to try and explain what some of the subtleties with state dependent operators are too, because I don't think we should be blasé with state dependence and be happy to use it whenever, whenever we can. We should really be forced to use it, and then we should still ask, does it still make sense? Yeah. Yeah, effects are. No, it's not state dependent. HKL not state dependent. I'll explain at the end of this lecture if I have time. No, that doesn't make it state dependent. HKL are ordinary linear operators. I'll write down the formula at the end. Yeah. If you ask me, just remember to ask me at the end. Okay, good. So what do we need? Yeah. I said GXI. In fact, I'm going to demand something a little simpler. Okay. So since we expect that the dual bulk geometry has a horizon, just in the bulk, there's a horizon. This horizon is at u equal to 0. Is the yellow chalk better? You can see the yellow chalk clearly? Okay, good. Okay, so there's a horizon, and let me call this horizon u equal to 0. And then this is something that Raghu covered in his lectures. You can use, let's say you have a field operator in the bulk. Let's call it phi bulk. Then you can, or let's say I found such an operator. Let me just call it phi. Then I could take this operator that I found, and I could differentiate it with respect to u, and then with some, this formula is, I'm not telling you what, this is some smearing function, that's not important. And then I could define some a tilde operator. What this operator is doing is just taking the field and integrating it in a small region here, okay, about u equal to 0. So this is how you integrate a. And the way you integrate it is, there are some modes which look like u to the I omega that are oscillating very rapidly near the horizon as you go to u equal to 0. Okay? So if you think about this in tortoise coordinates, these are modes that look like e to the I omega r star minus t. Okay? And these modes are oscillating very rapidly as you go close to the horizon, and then you do this integral in the near horizon region, and you pick up some operators, and I'm just defining those operators to be a. These are what you would call right moving modes outside the horizon. Okay, so they're what you would call right movers. So you pick up some right moving modes just outside the horizon. And then you can do the same integral just behind the horizon. And this integral is defined not with a minus u. So usually the convention is you take u to be negative on this side and positive on this side. And you define this, and again with another function. The details of these are not important. All that's important is that the a tildes are defined here. Okay? And these are really, they're very closely related to the modes that you find in Hawking radiation. They're exactly those modes. So you just take the field and you integrate it with u to the I omega. It picks up a particular Fourier mode of the field. But the Fourier mode you want to look at is the Fourier mode in the log u coordinate. In the coordinate that goes to infinity as you approach the horizon. The reason you don't have to integrate very far out on both sides is because you're trying to pick up a mode. This mode oscillates many times near u equal to 0. And therefore, it's enough to do the integral in a small region to pick up the mode with sufficient accuracy. Okay, so I'll label these modes with an omega, and I can discretize them so that they're not delta function normalized. And what I really want, there's only u in this formula. There's no v. There is no v. All these are u's. This is also u equal to 0. And so this is integrated for small positive u or small negative u, and this is integrated for small positive u. Now what I tell my kids, this is a joke some students have heard, is that when they're in school, it's important that they get their handwriting right, because it's their problem if their teacher misunderstands. But once you're old enough, then it's everyone else's problem if people take your u for a v. Okay, I hope this is clear, and I apologize for my handwriting. I've suffered a lot for it in life, but hopefully, I'll try and minimize your suffering. Okay. T is a smearing function. I'm not going to give you details of T. It's some function you need to regularize these modes to make them not delta function normalized. If you open this paper, long paper, this T is defined in detail. Okay. I don't want to go into what the details of T are. T is indeed a smearing function. It's kind of flat for some u. It's just all that T does is it makes this integral die off smoothly beyond some point in u. Okay. So T is like a step function. It's something, it kind of has support here and yields the support smoothly. That's all it is. Yeah. No, at the horizon also you can make it go to 0, but exactly at the horizon, but you want it to have support near the horizon. So you want to pick up a lot of modes from near the horizon. Okay, good. So what do I want? When I wrote there, I want some correlators to be like effective field theory. Really, I'm only going to put conditions on these A's and A tildes. Okay. So these are the conditions I'm going to put, and in fact, let me write them here because they'll kind of be sitting around. They'll play a role throughout these lectures. Okay, so what we want is first that there's an order 1 by n in all the formulas I write down, okay, and I'm not going to write it again. All these formulas, I want them to hold, but I only want them to hold to leading order in perturbation theory, or to zeroth order in perturbation theory. Okay, I don't want anything to hold to higher orders in 1 by n. So this is just a statement that these are some modes which are canonically normalized, and that makes sense if you have approximately free fields near the horizon. In fact, we do expect that the bulk is a very weakly interacting field, because remember in ADS-CFT the only coupling constant is 1 over n. So if n is large, everything is weakly interacting. Okay. So you have approximate particles. We also want this for, and I'm not writing the 1 over n. These modes commute. So the A omega tildes commute with the A omegas. The modes behind the horizon commute with the ones in front of the horizon. And then we want some 2-point functions. These 2-point functions should be thermal. Okay, and then there's some order 1 by n. Again, actually it's there everywhere, so let me not write it. And then we want same for A omega tilde dagger. Okay, this is equal to this 2-point function is equal to this. And then we want this 2-point function for the cross correlators, which is A omega tilde, A omega is equal to okay, this 2-point function is important because this tells you there is an entanglement between the inside and the outside. In fact, you can use this 2-point function to extract Bell pairs between the inside and the outside. So the correlators outside, or the operators outside, are correlated with themselves. This beta corresponds to the beta of the black hole, the temperature of the black hole. It also in the CFT corresponds to the density of states, which is, as I explained to Sumilan, it's the formula there. It's something you can define even for a pure state. And this is telling you that the modes outside are thermally occupied, the modes inside are thermally occupied, and the modes outside and the modes inside are entangled in a specific form. And this is also equal to A omega tilde dagger, A omega dagger. Okay. So there's a temperature, and this frequency omega keeps appearing everywhere, and the frequency omega was defined here. Okay, it's telling you how you're integrating the modes. Okay, and then there's one more important condition we are going to demand. You see, And this is where the first time where we'll go a little bit beyond trivial order and perturbation theory. So when I ask for these questions of what is, these are some effective field theory correlators, I have to be careful of how I dress operators in the bulk. So in any theory of gravity, it's important that, if I say I'm at this position, you have to make that gauge invariant. Okay? So I want operators which are dressed to the right boundary. Why do I want those operators? Because I want to ask the question of what happens to the infalling observer who falls in from the boundary. So saying that, so the way I define the position, the point x, is I drop some geodesic from the boundary and I let it run for some amount of time, and then I say this is what I call the position x. What that does for you is it tells you how these operators have to transform under large diffeomorphisms that do not vanish at the boundary. And in particular, the following relations are important. This h is actually a mode of the metric. It appeared in Tom's lecture today morning. And it's a mode of the metric at infinity. But what we are going to demand here is there's some commutator of the Hamiltonian with these operators, and it's this. Okay. This is the right Hamiltonian. Right now I'm talking about a single CFT, so there's only one Hamiltonian. Later it will be the right Hamiltonian. Okay. This tells you that this operator A omega destroys energy omega. Therefore it's an eigenstate of the Hamiltonian up to terms of order 1 over n with energy omega. This operator, which is behind the horizon, in fact, this is what sometimes is said, has wrong energy. But really, all this is saying is that, if you dress these operators to the boundary, like you had a boundary here and you dropped some geodesics here, and then you did a large diffeomorphism so that you shifted things by t, then, you would shift these operators inside also by the Schwarzschild t. And if you just go through these definitions, you will find that the operators inside have the wrong commutator with the Hamiltonian. Okay? And for A daggers, it's the obvious conjugate of this. So H A omega dagger is plus omega A omega, and H A omega tilde dagger is minus omega A omega tilde. Okay, sorry. Yeah. Okay. So all I want is that I should find some operators that satisfy these relations. Okay. So let me write this one for completeness. Okay, so I wrote a question there, which is, can you find some operators that have this property? I'm going to reduce the question now, and I'm going to spend the rest of the lecture, this lecture and the next lecture, saying, can you find these operators in the CFT? If you find these operators that have these 2-point functions, the conditions I'm demanding are really conditions on 2-point functions. This condition you might say is one higher order in perturbation theory, but it's still this condition. And this is all I'm asking for. Okay? Can you find operators that satisfy these properties in the CFT? If you find such operators, then we are happy. If you can't find such operators, we have a problem. Sorry, there are 2 questions. The state is the state psi. So these are CFT operators, and these expectation values taken in the state psi. These expectation values are all taken in the state psi. That is written there. Yeah.
Sorry, A omega dagger.
Yes. Oh, yes, indeed. Yes, sorry. Yes, correct. Thank you. Yes.
They're in the thermophile double, right?
No, these operate in a single CFT. You see, in the single CFT, you can find such operators, right? You take the field and you integrate it a little bit on this side, a little bit on this side, and there's a 2-point function of the field. And so such operators have to exist also in a single, when you define these operators in the bulk, you don't know if you're in a thermophile double or not. You just define them by taking the field and integrating them a little bit this side and a little bit this
Psi
side.
was a typical one-sided state on the boundary.
Yes, psi is a
How
typical.
do we know it has a behind the horizon?
Oh, good. So if it doesn't have behind the horizon region, then we'll declare it as a firewall or something. So this is the assumption. When I say gx1, I'm assuming that the geometry in the bulk is the geometry that corresponds to a large one-sided black hole, both outside and at least some distance behind the horizon inside. If we find that and indeed we'll find A omega tilde don't exist, then one answer you could give, which was why these paradoxes was first invented, was typical one-sided states do not have a horizon, do not have an interior at all. So that would be one way you could resolve this. That's why I also want to emphasize that in the thermophile double also we'll find a problem. Yeah. So if they do have an interior, then such operators should exist. It's a question of what assumptions you put in that G. You see, I said here that you should get the answers computed from effective field theory. Here I'm assuming the answer is computed from effective field theory, assuming a smooth interior. So I'll try and argue that's not possible. And also it's not possible for the thermofield double. So it's not as easy as saying one-sided black holes don't have an interior. Okay, so is this clear? Yeah.
I have one question.
Yes.
That commutator, you want it to be valid exactly or inside a correlation function?
Inside a correlation function. Always inside a correlation function.
Okay.
I didn't write it, but
Okay.
inside a correlation function, but to good accuracy inside a correlation function. So everything I'll demand is always inside a correlation function. I never want anything to be exact. If you can find something that works for me approximately inside correlation functions, I'm happy. Oh, thank you.
Suvrat, I have a question.
Yes, please. Yeah.
Uh,
Go on. Yeah. Are you here or?
no, I am online.
Okay. Go on. Yeah.
So I have a question on the functions T of U.
Yes.
So you introduced this function T of U for the sake of convergence of any integral, or?
This function T of U is not important. It's important to ensure that these operators are not delta function normalized. I could have written a delta omega minus omega prime here. Instead, I wrote a 1 here. So this is required to smear the modes a little bit. If you did the integral all the way from u not equal to 0 to the boundary, you would get some modes, but those modes would have a delta function normalization. This is just required to smear the modes a little bit so that I can write 1 there rather than delta. But for the physics, this is really not important. If you open that review that I had referred to, this T of U is described in some detail.
Okay, so does that mean you are avoiding some physical contribution for the physical?
Yeah, we are demanding a very weak condition, right? We don't want to ask what happens far away from the horizon and so on.
Okay.
So this is if even this doesn't work, then what's the point of asking what's happening deep inside the horizon and so on?
Okay. Yeah. Thanks.
Yeah. Very slightly positive. So you can do this to infinitesimal cutoff basically. You go from that's because the mode oscillates an infinite number of times near the horizon. So you don't have to integrate very far in to get a pretty accurate frequency mode. Yeah. Both those cases. So you integrate from u equal to 0 to u equal to minus epsilon and u equal to 0 to u equal to plus epsilon. The a omega tilde is defined by integrating from u equal to 0 to u equal to plus epsilon. Yeah, you have to go very close to 0 because you see, you're trying to pick up a Fourier mode. So you use the fact that the mode is oscillating an infinite number of times. So you take advantage of that. That's what lets you pick up a sharp frequency. It's a question of how sharp your frequency is. That will control how sharp this omega is. If you don't integrate too close, you'll get a thickness of frequency. So it won't be a single frequency that appears here. So that number you're talking about, how close to u equal to 0 do you have to go, will tell us how sharp that frequency is. A tilde and A are defined very close to each other, yes. They have to be slightly separate in the transverse coordinate also. Yeah. I urge you not to spend, we can discuss these modes, but this is really a topic for different lecture. But, again, these details are there. So this T of U is not physically important for anything I'm talking about. Okay, good. So now let me give you some statements about how you get these modes. First, let me say something about A omega. Okay? Let's say I forget about these A tilde omegas and I only want the A omegas. Okay? The A omegas are actually pretty easy to get. You get them by upgrading HKLL a little bit. And there's a concrete formula you can write down. And that formula is pretty simple. There's a standard ADS-CFT dictionary that tells you that for propagating fields in the bulk, you have some primary operators in the boundary. And you can take those operators in the boundary and you can integrate them, you can extract their Fourier modes, and you have to smear those Fourier modes too, as we discussed. And then let's call this boundary operator O omega. This is the mode of a generalized free field. And then you have to divide it by some normalization factor that I call C omega that corresponds to the commutator. And if you do that, you will find that you will get a mode that has the right properties. Okay? The fact that the boundary operator is thermally occupied, that it has this kind of occupation number, once you, So the important part of this occupation number has to do with, how this occupation with A omega dagger behaves with the occupation with A omega dagger A omega. Okay, and that one is down by a factor of e to the minus beta omega, and that just follows from the KMS condition that Raghu discussed in his lectures. And so the fact that the boundary operators satisfy the KMS condition in the typical state is sufficient to tell you that once you normalize the commutator correctly, then you'll get the right 2-point functions for A omega. Okay, so even if you didn't understand everything that I just said, the punchline is just that this is basically a version of HKLL. You take the boundary operator, you integrate it in frequency, and you normalize it in some way. If you do that, you will get operators that satisfy this condition and this condition. Okay? So the subtlety really has to do with modes behind the horizon, not modes in front of the horizon. Those are very easy to get. So that the answer to that question, if I just ask questions about correlators outside the horizon, is yes, and the answer is you get it by just doing this, taking the boundary operator, extracting its Fourier mode, and dividing it by a function that we can compute explicitly. Okay, that's C omega. Okay, so the question is really about, this is a boundary, single trace operator. Okay, are there any questions about these A omegas? What I've told you right now is I wrote down some conditions for operators that I had to find, and then I told you that it's very easy to find the operators outside. You just get it by HKLL. Yeah.
I'm still a bit confused. So the psi is a CFT frame.
Yes, yes.
And in the left-hand side of the equality on the far right board,
Yes.
the x1s are bulk points,
Yes.
which are also allowed to go behind the horizon.
Yes.
So you're assuming that the bulk dual of all of these guys has a behind the horizon.
I'm not assuming, I'm asking if you can find such operators. If you can't find such operators, then one valid conclusion, which was the conclusion here, would be that the bulk dual doesn't have a behind the horizon. So okay, if you like, I'm assuming, and then I'll proceed with that. If I run into a contradiction, I'll find my assumption was wrong. So you're right, you can say it that way. But in fact, these papers were initially written to say that the bulk dual doesn't have a behind the horizon for single-sided black holes. Yeah. So that it has a firewall as a. Okay. So is it clear you can find operators outside the horizon? Okay. So the question is, can you find these operators A omega tilde? Okay. This is not exactly how things were phrased in the AMPSS papers, but it's the way I like to phrase them. Okay. So now I'm going to give you some puzzles that say that. So AMPSS and Marolf-Polchinski SS say that the A omega tildes do not exist. Okay. So there's no discussion about the fact that the A omegas exist. This, by the way, is not state dependent, as I'll say in the end. It might, this number does indeed depend on the temperature and so on, but I'll tell you how to write it in a completely linear operator. But the subtlety is about these operators behind the horizon. Okay, so the claim was they don't exist, and then I want to explain what the puzzle was. So I'll give you two different puzzles. This is one that I call the negative occupancy paradox. Actually, I think this paradox might have been first set up by Kyriakos and me. It's some version of a paradox that appears in the AMPSS papers. But anyway, it's very closely related to these guys. I think it's in that 1503 reference that I gave at the beginning. Okay, so the claim is that you can never find these operators. So here I'm going to give you an argument why. So you see, we know that psi A omega tilde dagger psi. Okay. That this, just by very general kinematical arguments, if these are any operators in the CFT, for a typical state, it's equal to 1 by e to the s, okay, and then trace or sum over that same set of energy eigenstates So notice in this term, the cross terms have all dropped out. You might have worried about, I wrote a state which looked like sum of AI, EI, and how did I find this? The step of going from this to this is a general kinematic argument that you can find in many papers that tells you that Haar typical states are exponentially close to the trace in the microcanonical ensemble. Okay? So here we are using the fact that Haar typical is equal to microcanonical. Okay. So if this is true in it, whatever these correlators are in a typical state, that's also the value they take in the microcanonical ensemble. Notice what I'm doing here is, I'm taking the density matrix which looks like sum of EI, and just taking the trace with that density matrix. This e to the s is meant to normalize the density matrix to 1. Okay? Then by the equivalence of ensembles, this step is exponentially close. I can in fact argue that this is the same as 1 by z of beta. So I actually started out with a pure state, and this step follows by equivalence of ensembles, which is a standard result in statistical mechanics. Shumilan here will explain any questions anyone has about equivalence of ensembles. Okay. So we've gone from this pure state to this statement, which is now a statement about a thermal state. Okay. So the statement is whatever value these correlators take in a typical state is the same as the value in the microcanonical ensemble after exponentially small corrections, and by equivalence of ensembles, it's the same as the value in the canonical ensemble. Okay, up to 1 over n, and this step is only accurate up to 1 over s. This step is exponentially accurate, but we are dropping all those terms anyway. So I'm going to drop this guy also. Okay, good. However, now we have some trouble because let's take that trace and let's play with it a little bit. Yeah. It's over this range that I wrote here somewhere, which I just erased. If you ask me. No. So this psi is a hard typical state. This psi looks like where this I is in a range of energies, say 10 n squared to 10.1 n squared, or some other range that you like. That sum over I is the same sum over I that appears here. It's not obvious that this expectation value is the same as that, because this expectation value has these coefficients and cross terms. But you can argue that indeed it is the same as that. That's some standard kinematical argument. Okay? So this step is not obvious, but it's a standard step going from hard typical to microcanonical. And this is a standard step also going from microcanonical to canonical. Now, by the way, in all of these paradoxes, you might decide to question any of these steps. You might say, maybe these operators are such that this step doesn't work, maybe equivalence of ensembles doesn't work, and so on. I've never found that that leads to something useful, but there are these steps you're making which all rely on some assumptions. Okay. Yeah. No, this equality actually, which, you mean this equality? The correction terms to this equality involve the standard deviation. So what they in fact involve is the 4-point function of phase. So you don't, this equality works for all operators. The correction terms here involve the standard deviation. So as long as 4-point functions of phase are not exponentially large, this equality would not have a problem. If 4-point functions of phase are exponentially large, then you will find a 4-point function is giving you things that make no sense. Okay, so then you'd be in trouble anyway. So even though I'm making demands about 2-point functions, I am assuming that 4-point functions are not exponentially large and so on. That's what the correction terms involve. They don't rely on any notion of simplicity or the operators being simple or complicated. They are, statements about the Hilbert space. Okay, good. Now, let's say that's true. However, remember the trace is cyclic, right? So the equality is continuing here. This I can write as A omega tilde dagger e to the minus beta h A omega tilde. Okay? So I took that A omega tilde to the other side. This is just by cyclicity of the trace. Okay? Okay, good. Now I'm going to use the fact that I know the commutator of that A omega tilde with the h. That's the commutator I wrote here. Right? So acting with an e to the minus beta h here, and then acting with an A omega dagger is as if I had acted with an A omega dagger here and put an e to the minus beta h, but I just have to take out a special factor of e to the minus beta omega. Okay? Okay? But now, you know, I also know what the commutator is. So this looks like and this is actually the object that I started with, if you look at that board there. Yeah. So I started with A omega tilde dagger, and I've got back A omega tilde dagger with some factors of e to the minus beta omega. Okay. So I can in fact solve for the expectation value of that, and if I solve for the expectation value of that, the answer I'll find is, the prediction I'll find is that this is equal to, I'm just going to solve, is equal to e to the minus beta omega by 1 minus e to the minus beta omega with a minus sign. Okay? And that's just manifestly absurd. It's manifestly absurd because not only is it not the value that we wanted, you see the value that we wanted was that A omega tilde dagger was equal to this. Right? So first of all, not only did we not get the value we wanted, we got a negative value for a positive operator. This operator is manifestly positive, it's some operator into its conjugate, it's a positive operator, and we got a negative expectation value just by running through this set of steps. Okay, so this is obviously absurd, and this would tell you, would suggest that maybe such operators don't exist. Yeah? Here, this one, yeah, or I can say it here. So what I did is, I took this A omega tilde dagger and I moved it to the left. So I cycled the trace. Then I took the A omega tilde dagger through the e to the minus beta h. That gave you a factor of e to the minus beta omega. Then I took it through the A omega tilde by using the commutator. And then I solved for this, because now I have A omega tilde dagger on both sides. And if you do some simple algebra, you'll find that it's this. So it's not the value that you want. In fact, it's an absurd result.
What is this Hamiltonian you introduced? Where
This Hamiltonian is a CFT Hamiltonian.
CFT Hamiltonian. Then how did you find a commutation relation?
Because I demanded the commutation relations here. You see, that's what I said at the beginning. I said, I want to dress these operators to the right CFT, and that tells you that if you do a diffeomorphism on the right, these operators have to transform in a certain way, and that gives you these commutation relations. This is the statement that's colloquially sometimes made that particles behind the horizon have negative energy. But that statement is a very imprecise statement. It's really this commutation relation. Yeah?
Can you remind me why A tilde is expectation values of that form? Not that one.
This one.
This one.
Yeah. This has to do with 2-point functions across the horizon. We'll now use this one. I have not used this so far. Right now I created a paradox with this one. I'll now create a paradox with this one. This has to do with the fact that the 2-point function across the horizon is smooth.
Exactly what that is. So far you just used
Just this.
just inside mode.
Just inside, right. So the
Seems
already seems to give you a problem. That's right.
Suvrat?
Yeah, oh, sorry, yeah, go on.
I have a question on the equivalence of ensemble averages.
Yeah, okay.
So actually this equivalence reminds me of when one restricts Minkowski vacuum to a Rindler trajectory, then something like this happens.
No, the equivalence of ensemble is just a general result in statistical mechanics. Anything you compute in a microcanonical ensemble is the same as the canonical ensemble up to corrections that are suppressed by the entropy. And so it goes to 0 in the limit where the entropy is large. Here the entropy is order n squared.
Okay.
It's just some result in statistical mechanics. It's not.
I think the first equivalence
This
I'm
one.
okay with, even if this A tilde operator was a very, let's say, very spread out operator, then is the microcanonical equal to the canonical for such operators?
I think so, because it's a very general statement, again relies on the standard deviation of the thing. But as I said, maybe you could ask this question. You could say, maybe these operators are so special that for these operators, the equivalence of ensembles doesn't work. The correction terms that appear in this are always, I think, have to do with the standard deviation of the operator. So here it's suppressed by the exponential, here it's suppressed by the entropy. So I think if you demand that this operator is good and squares of this operator have good expectation values, I think that is enough to give you the equivalence of ensembles. Because when you do the equivalence of ensembles, you drop some correction terms. And those correction terms have to do with how much the operator varies between different energy
eigenvalues. Saddle point equations.
Correct.
Right. And then if you have an insertion in before that exponential, which is big, then that can shift the saddle point around.
Yeah, so it could be that these operators somehow have very different values in different energy eigenstates, right? That's what you'd be saying, that one energy eigenstate they have one value, another they have a completely different value. So, that would give you you would be able to detect that by looking at fluctuations of this observable. And, if this 2-point function, if you forced it to become correct by saying somehow there's a correction term here, then you'd find that the microcanonical fluctuations would be huge of this. So you'd find that, 4-point functions of the field are just giving you nonsensical results. So you want, so I think it's not so, we can try all of these things, but I don't think these things have ever been worked out and shown to lead to anything useful. Yeah.
So, but even if we forget about those steps, isn't the quantity, second to last quantity you wrote, the expectation value of a positive operator in the canonical ensemble
has to be positive, that's right.
Even if we forget about
that, okay, fine.
You've already got a problem.
Already got a problem, you're right. So already you've got a problem. Indeed, the problem is actually pretty simple to understand. The statement is that,
So this problem is coming because of that.
Exactly. So it's coming by saying that, the commutator structure came from effective field theory in the bulk. It came from the fact that in the bulk you demand some canonical commutation relations, and so you get a commutator. But in statistical mechanics, what it's telling you is that the creation operator has negative energies. So that's what is leading to trouble. It's the fact that you're demanding that you have the negative sign came because you have a omega tilde dagger is equal to 1 and not the other way around. So negative sign is coming because you're saying you have some commutation relations between two operators, but the creation operator is lowering the energy. Okay? And that's always trouble because you always have fewer states at lower energies. So if the destruction operator has lower energies, that's okay because it maps some states to 0. But if the creation operator has negative energy, that leads to trouble because the creation operator is trying to raise the energy. It shouldn't be destroying any states, but in fact it has to map you to a smaller dimensional Hilbert space. And so that's the root of this problem. It's the fact that creation operators can never have negative energies. If you do that, you run into trouble. Because creation operators always map smaller Hilbert spaces to bigger Hilbert spaces. And that's inconsistent with the fact that, so if they have negative energy, they would have to destroy some states. So that's the root of the problem, indeed, as you said, if you forget about the equivalence of ensembles. Yeah. Okay, good. Let me give you another paradox. I'm running a little short of time.
Polchinski point out this paradox that long before Amps and everything.
Did he?
The 2000s.
Is that so?
Yeah, the last thing you said about the inconsistency of a creation operator lowering the energy.
I should have known that, but I didn't know it. Maybe he did. If you tell me the paper, I'll refer to it tomorrow. Maybe he did. Yeah. As I said, these paradoxes are really AMPSS paradoxes. Maybe he did and then he recycled it and these papers are better known. So if you tell me a reference, I will say it tomorrow. Yeah. Okay, good. In fact, I wanted to discuss one more paradox, but in the interest of time, which in fact has to do with, which would have utilized this 2-point function. But in the interest of time, I'm actually going to skip this. This is one paradox. I think it's already sufficient to show there's trouble. There are many other paradoxes you can construct. I can try and put these notes up online if you want to see these the other paradoxes. But they're not going to give you anything different. They're going to tell you that these 2-point functions lead to trouble. Okay. So what I'm going to do in the interest of time is in fact go to the eternal black hole. It's a thermal trace, no? It's trace of e to the minus beta. It's just not just a trace. It's a weighted trace. Well, okay, so as I said, that's you could again say maybe the thermal trace is divergent or something happens. These are all possibilities to explore. Okay, but it's a thermal expectation value. No, you expect it to be a finite number. Where's the divergence coming from? Yeah? It's a thermal expectation value. So it's high energy states are getting damped, exponentially damped. I mean, these are all things, we can always go to, I've been down the rabbit hole trying to explore all these things, but we can all Okay, good. So I'm going to, in the interest of time, in fact, since I have only about 10 minutes left, discuss how a similar problem occurs for the eternal black hole. So, just to summarize what I said so far. What I said so far is, if you take a typical pure state and you demand that there are some operators on a single-sided CFT that satisfy these 2-point functions, you run into a paradox. I've showed you one paradox, but there are many paradoxes you can construct along these lines. Okay, and they all have to do with this fact that these operators kind of have the wrong energy and they are behind the horizon. And there are, as I said, and some of them are in my notes, but I won't go through them in detail. The point that I want to emphasize in the last 10 minutes is one answer to these paradoxes might have been, as Raghu was saying, that fine, the A tilde operators don't exist. And in fact, that was the import of the AMPSS papers, which was, we can't find these operators. So these operators don't exist. Therefore, typical pure states do not have an interior. So one possible answer, so what they wanted to say was A tilde do not exist, which means typical pure states have no interior. If they have no interior, then I started by demanding that the correlators should be effective field theory correlators, and the demand that such operators should exist came from demanding that the bulk field should behave like effective field theory fields. If there's no interior, you don't need the A tilde operators. Okay, so this is one possible conclusion you can get from these kinds of paradoxes. Okay? However, I want to show you that that's not good enough, because if you did demand that, then you would not only find a problem with typical states, you would find a problem with the eternal black hole, which I want to show you now in 10 minutes. Yeah. Go on. Okay, so this is something which is not always appreciated, so I want to emphasize this point. Okay. Okay, so here's the point about the eternal black hole. Okay, so we want some operators that in this thermofield double give you some operators, okay, that describe the experience of the infalling observer in the eternal black hole. Okay, so the eternal black hole is this geometry, and I want to take the points x1, x2, x3, xn to be along the trajectory of some poor person who decides to end their life by jumping from the right. Okay, and I want to ask what happens while they're at the horizon and they don't know that the singularity is coming. Okay, so we want to ask, in the eternal black hole, is there a smooth interior or not? Okay, so most people would agree that even for pure states, if there's a problem, for eternal black holes, we expect that you should be able to find operators that have a smooth interior. I'm allowed to use operators from the left and the right and do whatever I like. I just have to still find these operators phi. When I sandwich them here, I should get a smooth interior. Okay, now I'm going to show you that this is also a problem. If you make the following, very simple assumption. That is, that if you make reference to only the right infalling observer, and not to anything else, then there is no natural origin of time in the eternal black hole. Now, in the eternal black hole, if you shoot in things from both sides, then there's some notion of relative time between the right and the left. But if you only ask questions about what happens to a right infalling observer, then there is no natural origin of time. So I'm going to demand something slightly stronger. I'm going to demand that those operators should have the property that if I time translate the whole trajectory forward or backward in time, I still get the right EFT correlators. Okay? And I hope this is a reasonable assumption. There are many ways you can argue it. From the bulk, there's a time translational isometry. This kind of time translation just corresponds to doing a large diffeomorphism. So if these operators don't see anything at 0 time, there's no reason why they should see something at time 100 or time 1000. Okay? I emphasize that nowhere in this, and this I'm going to demand is an exact statement even for large t, even for exponentially large t, but I emphasize that nowhere in this am I taking any of the time differences between these guys to be large. I'm just shifting the whole origin forward and backward in time. And then it would be very unreasonable to say, I like time 0, but I don't like time 10 to the 10. Okay? Because it's just an arbitrary choice of what the origin of time is. So I'm going to demand that not only do these correlators work in the eternal black hole state, but they also work in these time-shifted eternal black hole states, in that If I do a shift only on one side, nothing changes. Okay? Huh? This H can be HR or HL, it actually doesn't matter because HR minus HL is a symmetry, but you can take it to be HR. The exercise are here, but now the statement is if I shift the whole time, then I'll get a shifted trajectory which is somewhere here. Can you see? I just shifted it forward or backward. And that's the same experience. There's no origin of time. The black hole has kind of existed forever and will continue to exist forever, right? So if I decide to jump now or jump later, it doesn't matter. I have the same experience. At least that's the physical expectation. Yeah. The paradoxes always have to do with the interior. Yeah. No, I'm allowing you to use phi from both CFTs. I didn't say that the phi is an operator made of one CFTs. No, we don't know. There'll still be a problem. There'll be a state, we'll still need state dependence. No, we don't know such a thing. Well, the problem is that if, you see, from the bulk perspective, there's no problem for a single-sided black hole. The problem is when you try to embed these things in a finite dimensional Hilbert space with finite entropy, you run into problems. That's always the flavor of these paradoxes. It's not that from the bulk you see a natural, it's the same kind of paradox we'll find. Yeah.
So Suvrat, is it like you're changing the thermophile double state by giving a phase to
Yes, exactly. So these guys are so this state, these other states would be e to the IET.
Okay.
Or minus IET. Yeah. It's only the phase only matters up to 2 pi, so there are some phases that you get. IET mod 2 pi. Yeah, exactly. No, it won't cancel. There'll be cross terms. It won't automatically cancel. Yeah. Okay, good. So this is what I want to demand, and I want to show you this will lead to trouble. Yeah. It never reaches across the horizon. No, because the time to the horizon is always exactly the same, right? You see, if there's an isometry. If I change the time, we draw the Penrose diagram this way, but in fact the proper time from this point to the horizon is the same as the proper time from this point to the horizon. It looks longer in the Penrose diagram, maybe that's confusing you, but if you have an observer who jumps in, the proper time to reach the horizon is the same, whether you jump at earlier times or late times. And that's why it's an eternal black hole, it's always existed. So the Penrose diagram is a little deceptive because it looks like it's longer at earlier times, but it's not like that. If you calculate it, you can see. Okay, good. So let's say there's some operator A, right? Let me call this guy A for now, just to make something simple. Can I get 2 minutes more from the chair, please? Okay, I'll finish soon. Yeah. Okay. You see, let's say I have this operator. Actually, it's a question that Sandip asked. Okay. So you see, you get 2 terms when you do this. One term is the term where the phases cancel.
Are you using the orange or?
No, I'm using the yellow, but the lighting has changed. Actually, something they have to,
okay, I'll tell them.
Increase the lighting, please. There's nobody there. Thank you very much. So you get 2 terms. One of them is this term, which looks like a thermal term, and then you'll get some cross terms. Okay, the cross terms have the form 1 by z sum of E not equal to E prime, and then they have an E prime, A E prime, and then you have a phase factor. Actually, I'm sorry if it's hard to read, but the phase factor is just E minus E prime t. It's kind of the obvious phase factor. And then there's an E to the minus beta E. This is just I E minus E prime t. So these are just the cross terms. These are the diagonal terms, and then there are cross terms which just come by taking this and sandwiching an operator A between them. Yeah. Is this clear? I hope you. Yeah, it's legible also. Okay, good. Yeah. Now remember, I'm demanding that this should be independent of time because there is no origin of time. Yeah.
In the cat, you want L in the bra, you want.
Oh, thank you. Yes. Indeed, thank you very much. I want E and E prime. Thank you very much. Yeah. Sorry. You're right. It's e to the minus, I'm just trying to rush. I'm trying to rush too much. If you give me a few minutes, I'll not make typos. Okay, sorry. This thing is going to ring now. Okay, I'll try and finish very soon. This is a short puzzle. Okay. Thank you very much, very kindly. So this is the term that you get. Yeah. Okay. Now, I said that this should be independent of time. Now you might have said these states are energy eigenstates are exponentially close. But if you demand that it's exactly independent of time, even for times that are long, even exponentially long, and as I said, exponentially long is, there's no time difference that's becoming exponentially long. It's just saying that the origin is 0 or 10 to the 10, which you're allowed to always do. Then this term should really not contribute, because this is time dependent. So it must be that these operators, whatever they are that describe the experience of the infalling observer, receive contributions only from this term and not from that term. That's just a consequence of demanding that this should be independent of time. Okay, good. So it must be the case that these terms by themselves have the property that they give you the correct effective field theory correlators. Okay, now I'm going to make one more assumption, and then in fact the puzzle will be obvious. So Alok asked already, these operators can be in the left and the right CFT. Now I'm going to make another assumption that's kind of obvious, or at least we think it's obvious from quantum mechanics, which is EE, this state, which is not entangled, just this state, energy eigenstate on left, and energy eigenstate on right. Let me write it just to make this more explicit. Let me write it this way: direct product state does not have a wormhole. This is, if this is not true, then many things we think about quantum mechanics are not true. This is saying you have a disentangled energy eigenstate on the left, disentangled energy eigenstate on the right. Surely nothing you can do from the left should affect anything that you can do from the right. And if this wasn't the case, then some energy eigenstate we made here, or maybe Vijay will speak in the next session, that Vijay makes in his lab might, get affected by some energy eigenstate somebody makes somewhere else, which should not happen. If this is the case, then in fact, these correlators, just in this energy eigenstate, these diagonal correlators, which describe the experience of the right infalling observer, should not be affected by any left unitary. Because the right infalling observer never reaches the left, right? They end their life behind the horizon. And there should be, maybe in the eternal black hole we say you can shoot a shock wave and hit them. But, in the energy eigenstate, surely it should not be possible. So this is the statement that there are no wormholes in disentangled energy eigenstates. So these operators should
Finding
be...
it exactly or up to order?
No, this I think we want to demand exactly. We want that there should be, because it should not be the disentangled energy eigenstate. There is a way to influence what's happening on the right from the left. If that was the case...
Phi may have some component from the left, right?
Phi may have a component from the left. I allowed that to happen. But then I said I have a physical requirement, which is that in this kind of disentangled energy eigenstate, just a single energy eigenstate, the experience of the right observer should not be affected by what's happening on the left. So for a disentangled energy eigenstate, the experience of the right observer should be as if they're falling into a pure eigenstate of the right CFT.
Okay, but you are assuming that the same phis which will describe that.
Yes. So that's the question of state dependence.
I see.
But for now, I'm assuming that there is some phi that works everywhere in the Hilbert space.
Okay.
So if this is the case, then you find this is true. But if this is true, then these phis must really be operators only in the right CFT. And so now we have found that in fact these phis, under the assumption there's no wormhole open in disentangled eigenstates, are in fact operators only in the right CFT. Therefore this correlation function becomes automatically just the trace. So therefore I cancel off the cross terms by demanding time independence, and now I'm going to cancel off just has become the trace in a single CFT of this. Let me just recap how I went from this. This was some complicated entangled state. When I expanded this out, I got two kinds of terms. I got diagonal terms, which you see there, and then I got off-diagonal terms, which had time dependence. I said, look, the eternal black hole does not have an origin of time. Therefore, whatever correlators are describing the experience of the right infalling observer can't actually depend on the cross terms, because if they did that, I would use that to define an origin of time. Therefore, the cross terms can't matter. Then I said, look, in the disentangled energy eigenstate, there should be no wormhole open. Therefore, in the diagonal terms, can matter, but therefore they must be the same as just operators in the right CFT. They can't depend on what's happening in the left. So in particular, for instance, I can do a unitary that maps all of these energy eigenstates to the identity or to something else. And then that tells you that all the diagonal terms in fact collapse into a trace taken purely in the right CFT. But I already showed you that there are no operators in the right CFT that can give you the correct effective field theory correlators inside a canonical trace. We already derived a paradox some time back. So the single-sided paradoxes imply also a paradox for the eternal black hole under just a very reasonable physical assumption that first there's no origin of time, and second the disentangled states don't have a wormhole. So if we are willing to say that single-sided black holes don't have an interior, which we can say typical states, then we are also led to the conclusion that the eternal black hole doesn't have a smooth interior, or something goes wrong in these assumptions. Either disentangled energy eigenstates have a wormhole, which would be very weird, or the eternal black hole has an origin of time, which would also be weird. So Marolf and Wall also had a similar thing, which I've never understood, but it's roughly similar in flavor, I think. Saying that if disentangled states don't have a wormhole, how can entangled states? So indeed, there was also a prelude to the AMPSS papers by Marolf and Wall, which was along similar lines. Yeah. There is, because on a single-sided case also there's a notion of a black hole, of an observer falling into a black hole.
There is a secret third assumption here, which is that you're assuming that even though you created this observer purely on the right, why should we expect that when he falls through something that we call the Barth geometry, that should continue to be described by purely right?
I didn't make that assumption. I just said there's no wormhole in the disentangled energy eigenstate. So I didn't start by the assumption that the operator was described only on the right. The operator could have been a combination of right and left. Then I said, whatever operator you're using, you can use whatever combination you like, right and left. Just make sure it has the property that when you use these operators in the disentangled eigenstate, I cannot affect the observer by throwing in something from the left. So you can use whatever operators you like, right and left. But make sure that in the disentangled energy eigenstate, I shouldn't be able to send a message to the observer. So we agree in the entangled state there's a wormhole, but we also agree in the disentangled state there's no wormhole. So, that then led me to the conclusion that the operator had to be an operator on the right. So it's important I didn't put that assumption in from hand. I put it in by physical assumption, which is this. It's this assumption that led me to that conclusion. And plus the fact that the cross terms can't contribute, which is coming from time translation. So that leads me to the fact that there's a paradox also for the eternal black hole. So you'll have to violate something. Either you have to tell me this has a wormhole, or you'll have to tell me that the eternal black hole has an origin of time. Okay? Or, in fact, let me just say something and I'll stop. So let me just say one thing and I'll stop. Yeah. So of course, in all of this, we have been assuming. So this was the argument of the original arguments were due to AMPSS. The argument I presented for the eternal black hole was due to Kyriakos and me. But in all of this, we've been assuming that look, it's the operators. These operators phi are operators that you define once and for all in the Hilbert space. And therefore, I can use the same operator in the thermofield double that I used in the disentangled energy eigenstate. Okay? And one possibility is that maybe that's not the case. Right? Maybe the operators are state dependent. Okay? However, I want to emphasize, as I said, even though state dependence is nowadays used a lot, it's really a rather radical statement from our, if you looked at the postulates of quantum mechanics, you open Dirac's book, you would find the statement that observables are some linear operators that are defined once and for all for the Hilbert space. They're not defined with respect to the state. So, the option that I want to explore tomorrow is that you can also resolve these paradoxes while keeping a smooth interior while allowing for state-dependent operators. So I'll write it here and then I can stop. Okay. And then I want to explain how there are subtleties which are still unresolved, which have to do with issues of state dependence, but I'll explain that tomorrow. Okay, so there was an assumption in all of this that, let me emphasize one more thing. The way we derived the paradoxes was always by taking a trace. All the paradoxes always involve a trace. They're never paradoxes that are, set up in one state. The other paradoxes that Marolf and Polchinski had also always involved a trace. And if we allow our operators to vary with the state, then those paradoxes go away. Okay, but then we have to deal with other issues, which I'll describe tomorrow. Okay, but I wanted to tell you how today you're forced to one of several different possibilities. Either you have state dependence, or you have no interior for a typical state, but then you also don't have an interior for the thermofield double. And the last point I really want you to keep in mind, it's not enough to just say typical states are bad. You also will have to give up the canonical example we have of ER equals EPR. Okay, I'll stop here. Sorry for going over time. Thank you.
We already have many questions. We'll take questions till what? At least 5 minutes and then we'll close. Okay.
No. For the off-diagonal, well, you have to take a special operator, but it's a physical requirement I'm getting from the bulk. So whatever operator it is has to have the property that the off-diagonal terms don't contribute. So if you, by the way, look at operators which are entirely on the right CFT, then it's obvious the off-diagonal terms won't contribute. Yeah.
Just wondering why state dependence is such a big problem, because we know that in gravity local operators don't exist, right? So the operators that we're trying to construct are only in some approximation.
Yeah.
So why should we worry about having state dependent?
It would still be unusual because you wouldn't have, we can discuss this tomorrow more, because we don't have a measurement theory for these operators. The usual way we describe how an operator measures, how something is measured, is we add it to the Hamiltonian. But we don't want to add these operators to the Hamiltonian. And also this state dependence seems to occur only behind the horizon of a black hole. It's not something, this statement that we don't have local operators in gravity is true even outside the horizon of a black hole. But there we don't seem to need this kind of state dependence. So, it's something that has to do with, as opposed to what I said at the beginning, which had to do with loss of locality in gravity, where we have said operators here can be identified with operators around that. That's a feature we can see in empty space. It follows from the constraints. So it's a general feature of gravity, which is that operators in a bounded region can be identified with operators in the complement. But state dependence somehow seems to rely really on the presence of black holes. So it's somehow something special. At least I don't know any other example where you need state dependence. Of course, I agree with you that it's perhaps the right, might be the right thing, but I just want to emphasize it's something we should think about because it does challenge some notions of quantum mechanics. Maybe Jonathan can say more. We've had many discussions on this, but yeah.
Suvrat,
yeah, of course, yeah.
in the SYK model, the state-dependent operators were naturally introduced by Maldacena and Kurkut.
Yeah.
I mean, it's a very natural thing to do to describe black hole physics there.
Yeah, I mean, naturally something, it's true that, you can introduce these projectors and have these state-dependent operators. I mean, natural is a subjective thing. The question is, here also we might say they are natural. We'll discuss them tomorrow, but the question is whether, whether you should allow them. And the reason I've gone through this in detail is just to emphasize, at least for some of the younger people in the audience who might not have been around when these discussions were being had, that you're really forced to them, or you have to give up something else which you think is very dear to you. Yeah.
Several hands. Let's take one from the front.
Over here.
Yeah.
So pi could have been from the left-hander, right?
It could have been in principle, although we find it can't be because of this condition. It could have been, but this equality tells you it is not.
Yeah, I'm trying to look at why this is an equality. Right?
This is an equality because of this physical assumption that this state does not have a wormhole. Because it doesn't have a wormhole, if I had something from the left boundary, you would never be able to find an operator which commuted with all unitaries on the left. So if I had some contribution from the left boundary, then this would not be an equality. If it was not an equality even for the energy eigenstate, then you would violate this physical assumption.
I think he's asking what are some of the x's on that?
Yeah, that's
Oh, some of the x's are on the left. No. Here I'm talking about an infalling observer who falls in from the right. I'm demanding that you have the experience of an infalling observer who falls into the right. They still see an energy eigenstate. They fall in, and you should not be able to hit them with something from the left. This is what this is telling you. This is shooting a shock wave. Okay.
You initially started with just a statement about correlators, psi, psi.
That's right.
And then where did the infalling observer come in?
No, this, yeah.
That's one. And then the second question, in this A operator that you wrote,
Yes.
if you demand this is independent of time, this is saying that H commutes with A, right?
This is
Take a derivative with respect to time.
no, because if A doesn't map, no, it doesn't demand that. Because, okay, go on with it. It doesn't imply that, because notice if A was an operator, for instance, only from the right CFT, then it give you 0 in these states, because these are states which have E prime. You see, the states here, the cross terms that you get look like E, A, E prime. So it doesn't demand that, in fact, it's also leading you to this conclusion that if A was an operator only on the right, then it would have 0 matrix elements between any such states, because it can never change the state of the left.
I mean, just take a derivative in the first line.
Yeah, but you can see that I can take any operator A which is only on the right CFT. Only on the right CFT. It manifestly satisfies this condition. Because operators on the right CFT, this is a thermal state, right? So it's time translationally invariant. Because of this reason, you look at this cross term, here T drops out, and look at this term. This term has E on the left, E prime on the left, on the right. Oh, sorry, the state on the left is E here and E prime here. And this operator is only on the right, so it can never map E to E prime. Okay, but is it not clear? But okay. Sorry, where did I, yeah. No, I didn't assume that. But let me just answer one question which I forgot to answer for Raghu. Raghu, your first part of your question was where did the infalling observer come? I'll come to that question. The infalling observer is not, I was just using it as word for how you take these coordinates to be. The question was, I want these correlators to work out correctly all along the trajectory, provided I take x's to be coordinates, which could have been the trajectory of an infalling observer. So that's all I was saying. I was just saying that, you take x's to be along this line, like these are the x's, and I want the correlators to work out correctly for these x's. So I'm using the words infalling observer physically, but really the mathematical statement I want is that where you take x's to be along any possible trajectory of the infalling observer. The question you had was, did we assume that E's were for a black hole? No, we didn't need to assume that here. We just needed to assume that whatever the correlators E are in an energy eigenstate, in fact, you do expect them to be that of a black hole outside, but whatever they are, they should be such that they are not affected by a shock wave coming from the left. So if you are in a disentangled energy eigenstate, then someone should not be able to shoot you by doing something from the left. It could be whatever. Maybe the geometry has a firewall. Maybe actually it doesn't. Probably we don't expect it to. But maybe the geometry is such that, let's say you define these operators in the following way, that you fall in for some proper time and something happens. Okay, let it be whatever the geometry is. Maybe the geometry is you go into some fuzz in an energy eigenstate. Actually, I don't think that's correct. Energy eigenstates, I think, should correspond to just smooth solutions, just like other states. But for the sake of argument, let's assume it was a different geometry. All I demanded here was that whatever geometry it is, the person from the left shouldn't be able to shoot you by shooting a laser that's as strong as they like. So whatever geometry it is, I didn't actually need to use. That being said, I think there's good reason to believe that energy eigenstates are also smooth. In fact, there's a paper by Kyriakos on what's the dual of an energy eigenstate, as smooth as others, as other states. So it's not that energy eigenstates are bad.
Yeah, I think we'll have to close here. Thanks
Okay,
a lot.
thank you.
Suvrat. 4:05, so you can have a cup.